Let's take out this this gauntlet problem. I trust that you've all tried to work this in your meantime. Does anyone need another copy of this? I've got parts A and B correct, so let's do that together. I have 3 blocks, C, B, and B, and we're told that A is a small block, that B has twice its mass, and C has 3 times the mass of A. Now, the table is going to push up, canceling the weight force in every case. Now let's do the more challenging forces. I start with the simplest free body diagram, the thing that touches the fewest other things. That's block C. And the only thing touching it besides the table is B, and it pushes with a normal force. Now there's no friction between the blocks and the table. There's no friction required between A, B, and C for them to push on each other. So that's our diagram. Now I go to B. If B is pushing to the right on C, then C is pushing back just as hard on B. And I would use tick marks to indicate that those are third law companions. Now the only other thing touching B is A, and it's pushing with a normal force. And I drew this bigger than this because if I look at this diagram here, for C, it's screaming to the right. If I'm pushing on these blocks on a frictionless table, that's going to cause all of this, A, B, and C, to accelerate to the right. And so that means this diagram must also scream to the right. Now I do my diagram for A. If A pushes to the right on B, then B pushes just as hard back on A. I put 2 tick marks there, 2 tick marks there, and then finally the hand pushes on A. And those are my free body diagrams. Now part B asks us to identify any third law companions. Well, we've done that. That was easy. We actually used third law to draw our free body diagrams. Now part C of this gauntlet, where people started falling off the bus, asks us to rank the net force on A, B, and C. Now folks, when you're ranking net forces, don't go to the free body diagrams. The net force is not on your free body diagrams. It's not a real force. The net force is the vector sum of all the real forces. What you should use instead is Newton's second law. F net equals ma. And ask yourself what's the same and what's different. Well, if I'm looking for the net force on A, this is the mass of A and the acceleration of A. Well, B has the same acceleration. They're moving together. But B has twice the mass. So it's going to have twice the net force. Likewise, C has the same acceleration as B and A. They're moving together. But C has 3 times the mass of A, and so it's going to have 3 times the net force by Newton's second law. Now, does that make sense? Okay, you just got through half the gauntlet. Now this isn't on the gauntlet, but this is something that I think you should know. If I were to tell you that this force here, the normal by B on C, was 15 newtons, could you tell me how many newtons each of the other horizontal forces was? Don't worry about the vertical forces, just the horizontal forces. Okay? With your neighbor, find the rest of those forces. How many newtons are they? Okay, let's do it together. The key is recognizing what the net force is on each of these objects. If I look at block C, this cancels that, and the net force is this only single horizontal force. So that means that the net force on C is 15 newtons to the right. Now I said the net force on A was 1/3 the net force on C. So that means that this diagram has to screen to the right by 5 newtons. That's the F net on A. Now the F net on B is twice the F net on A, so this diagram has to screen to the right by 10 newtons. That's the F net on B. So let's make it so. If that's 15 newtons, by third law, this is 15 newtons. They're third law companions. This diagram has to screen to the right by 10 newtons. So this force has to be 25 newtons. 25 minus 15 is 10 to the right. If this force is 25, so is this by Newton's third law. This diagram has to screen to the right by 5, so the hand is pushing with 30 newtons. Okay, it's that easy. Check that your neighbor understands that, please. Okay, now it gets challenging. We replace block B with a block D that is much, much lighter, has less mass. And we push with exactly the same push that we had before. And the question asks us, the next question, asks us about the acceleration of this system compared to the acceleration of that system. Now, twice in your tutorial, you did something that simplified the problem. You lumped things together in a system if they were moving together. And that makes your free body diagram simpler. If we lump all of me together as a unit, then we don't have to worry about the force by my spleen on my liver or my liver on my spleen. Those are internal forces, okay? Only external forces go on your free body diagram. So if I lump A, B, and C all as one unit, the only things that act on A, B, and C are the earth pulling down, the hand pushing to the right, and the table pushing up. These internal forces of B on C and C on B and A on B and B on A, they don't enter. Now if I do the same thing for A, D, and C, you'll see that the mass is smaller, so the weight is smaller. The table is pushing less. But the net force is the force by the hand in magnitude. The up cancels the down in both cases. So both of these diagrams have exactly the same net force, namely the normal by the hand. However, the system on the right has less mass, and hence to make that equation equal, I have to have a bigger acceleration. If my acceleration initially was 3 meters per second, it's now got to be something bigger than 3. Bigger than 3. If you push the same on a Cadillac and a Volkswagen, the Volkswagen speeds up at a greater rate. Make sense? Let's go to the next part. The next part asks us about the net force on block A and block C. These are the two blocks that don't get changed. How does the net force change as we replace B with block D? Well, let's look at block C. The argument's the same for block A. If I am looking at net forces, I don't go to the free body diagram. Instead, I go to Newton's second law. And I ask myself, what stays the same? Well, does the mass of block C change when I change B for D? No, C is still the same block it was before. Its mass stays the same. But now that block C is accelerating at a greater rate. How's that going to happen? In order for that to happen, I've got to have a greater net force on C. A greater net force. The same argument can be made for block A. It has the same mass, but now it has a bigger acceleration. It must have a greater net force. Now, if I look at the free body diagram for C, I can see that this has an important consequence. Since the diagram for C is very simple, the net force is just whatever's behind it pushing on it. If the net force has to be bigger when I replace B with D, that means the little block D must be pushing harder on C than the big block B was. Now this is where people fell off the bus. They said, well, B's going to push harder on C because it's bigger. Bigger things push harder. That's the kind of reasoning we don't want to use on the exam. Bigger things push harder. You know, Arnold Schwarzenegger pushes harder than Mary Lou Retton. That's a dated example. I'm sorry, that's not going to help you. Okay. We argue with free body diagrams, not with bigger pushes harder. Okay? Now, that tells us that the little block D is pushing harder on C. The last part of this gauntlet asks us to compare these two forces. Which is bigger? C pushing back on B or C pushing back on D? Well, we've already answered this question if we believe Newton's third law. I mean, we just compared these two forces, didn't we? Weren't those the forces that we just had on our free body diagram? And we said that D had to push harder on C than B pushed on C. That's where we just were. Well, by third law, this force is equal in magnitude to that force. And this force is equal in magnitude to that force. So if this one's bigger than that one, then that one has to be bigger than that one. So the biggest of the two is C pushing back on D. By third law. By third law. Check that your neighbor got all the way through the gauntlet. All the way through the gauntlet.